In the last 4 lectures, we have completely explained Maxwell's distribution law for molecular speed of a perfect gas. Now, our today's lesson is to find the value of the RMS speed, average speed, and most probable speed. Actually, according to kinetic theory of gases, the speed of molecules varies from 0 to infinity. And so in this condition, you can say that the speed of molecules is not constant, and so we define actually 3 values of the molecular speed, and these 3 values are known as RMS speed, that is root mean square speed, average or mean speed, and the most probable speed. Actually, RMS speed and most probable speed have been discussed earlier to some extent, but here we will discuss these things in very detail. And for this, again, you have to remember what you have learned in the previous lecture. So for your convenience, I am mentioning all those results which we have discussed in the previous lectures, and these results will be needed for the discussion of these 3 values of molecular speed. So let us see what we have learned in the previous lessons. The first result which I have mentioned here is actually the Maxwell's law of distribution of molecular speed, and this mathematically it is expressed as dnv equal to 4 pi n a cube e raised to the power minus bv square times v square dv. In this equation, a and b are actually constants at a particular temperature, and a and b are correlated. You have seen earlier that a is equal to a square root of b over pi, and we have obtained the value of the constant b, and this value is b equal to m over 2 kt. And so from this relation you can say that a is equal to a square root of m over 2 pi kt. Now we have also defined in the previous lecture a very important function which is called Maxwell's speed distribution function, and this is defined as dnv by dv. And so from this result you can easily see that this function fv is equal to 4 pi n a cube times e raised to the power minus bv square times v square. And you have seen that the probability that molecules will have a speed between v and v plus dv is simply defined as dnv over n. That is the number of molecules having a speed between v and v plus dv divided by the total number of molecules. And so again you can see from this result that this probability p of v will be equal to 4 pi a cube e raised to the power minus bv square times v square dv. And you have also seen 2 important Gaussian integrals which actually we need to solve our problem. And again I have mentioned those 2 Gaussian integrals here for your convenience. This is integral 0 to infinity e raised to the power minus bx square times x raised to the power 2n dx, and this is equal to 1 is into 3 into 5 and to so on 2n minus 1 over 2 raised to the power n plus 1 into a square root of pi over b raised to the power 2n plus 1. Here you can see x contains actually even power because 2n is an even number. So whenever such integral will be encountered to us, then we will use this formula to evaluate that integral. And again, when x has a power 2n plus 1, then this integral is simply equal to n factorial over 2b raised to the power n plus 1. So these are the results which we have clearly understood in the previous 4 lectures. Now, as I have told you, our aim is to define the 3 values of molecular speed, and those values are RMS value, average value, and the most probable value of molecular speed. So now let us start to find the expression for these values of molecular speed one by one. So first of all, we will see root mean square speed. In abbreviated form, you also say it RMS speed. As the name reflects, that what is this root mean square speed? Mean square speed, when actually we will find the mean of the square of speed of molecules, and after that we will take the square root, then you will get simply the root mean square speed. So we say that the square root of the mean square speed is known as root mean square speed. So if you consider that this v bar square is the mean square speed, again I am repeating that mean square speed means we will find the mean of the square of molecular speeds, and if this is v bar square, then in accordance with the definition of root mean square speed, we will take simply the square root of this v bar square, and then we get v RMS, that is root mean square speed. So mathematically we say that v RMS is equal to square root of v bar square. So you can see, if you want to calculate the value of v RMS on the basis of kinetic theory or on the basis of Maxwell's law of distribution of molecular speed, then definitely first of all you have to find the value of mean square speed, that is v bar square, and after getting the value of this v bar square, we will find simply the square root of it, and then we will get v RMS. So let us proceed how we can find the value of v bar square. As you know, this dnv, which appears in the Maxwell's distribution law for molecular speed, what does it mean? We have studied it in detail previously, and you know this dnv is what? This is actually the number of molecules having a speed between v and v plus dv. When you write the symbol dv, it means this is in an infinitesimally small quantity. So the difference between v and v plus dv, which is dv, is very small. So in this condition, we simply say that on average, the speed of each dnv molecule is simply equal to v. It means you can say, for just a practical example, let us consider there are 10 people, and the age of those 10 people lies between 50 year and 50.2 year. In this condition, in practice, we say that on average, the age of each 10 people is in fact 50 year. So in this condition, as dv is very small in comparison to v, so you can simply say that the speed of each dnv molecule is simply equal to v. And if you want to know the mean square speed, first of all you have to find the sum of the square of speed of all these dnv molecules. And so what will be the sum? As each molecule has speed v, so if we want to know the total sum of the speed of all molecules, then we will simply multiply v by dnv. But here we have to find the sum of a square of the speed. So first of all, we will take a square of v square, and then we will multiply it by dnv, and this product will give you the sum of a square of a speed of the molecules. For example, a practical example, as I have told you, that if you consider there are 10 students and in the pocket of each student there is 100 rupees, then what is the total rupees? That will be actually simply 10 into 100. And if you want to find the sum of the square of the money in the pocket of the students, then you will multiply simply by the number of students to the square of money in one of the pockets. So that will be simply 10 into 100 square. Similarly, you can say if we want to find the sum of the square of a speed of d and v molecules, and each molecule has a speed v, then we will simply square the v and multiply it by d and v. So this v square into d and v gives the sum of the square of a speed of d and v molecules. And as you know, in accordance with kinetic theory of gases, that the speed of molecules vary from 0 to infinity. And since the number of molecule is very large, so we consider that this speed actually varies continuously, not discretely. So if the speed varies continuously and you know the sum of the square of a speed of d and v molecule, and you have to find the sum of the square of a speed of all the n molecules, then what we will done, as I have told you that speed since varies continuously, so to get this sum we will simply integrate this result between the limits 0 and infinity. So this integral of v square d and v from 0 to infinity will give us the sum of the square of a speed of all the molecules n which are present in our gas. Now, in accordance with the simple definition to find the mean of any quantity, you know the mean square speed will be defined in this way. This is v bar square equal to sum of the square of a speed of total molecules, that is n molecules, and divided by the total number of molecules. And you have obtained that the sum of a square of a speed of the all molecules n is equal to this much, and total number of molecule is n. So what will be this v bar square? This will be simply 1 over n integral 0 to infinity v square d and v. Now in this equation we will simply put the value of this d and v from Maxwell's law of molecular distribution. So from Maxwell's law of molecular distribution, or you may say Maxwell-Boltzmann law of molecular distribution, you have seen and I have mentioned just earlier, and I hope now you can remember. So there is no need to turn over the page always to show that result. So definitely you have in your mind this result. D and V, you know this is equal to 4 pi n a cube e raised to the power minus bv square times v square dv. So now let us put this value of d and v in our equation number 2. So you can see this v bar square will be equal to 1 over n integral from 0 to infinity v square times d and v, and d and v is equal to 4 pi n a cube times e raised to the power minus bv square times v square dv. Now you should take the constant factor 4 pi n a cube outside of the integral, and you can see when we will do it, the n in the numerator and in denominator will cancel out, and our result will be 4 pi a cube integral 4 pi a cube integral 0 to infinity, and this v squared times v squared, this will be v4 times e raised to the power minus bv square dv. Now you can compare this integral to the Gaussian integral which we have mentioned just now. Here you can see this is the Gaussian integral containing x to the power an even number. So using this formula you can evaluate that very integral. Here you can see at the place of 2n there is 4, so n will be equal to 2, and if n is equal to 2 then this 2n minus 1 will be 3, so the result will be 1 into 3 over 2 raised to the power 2 plus 1 into a square root of pi over b raised to the power 2 into 2 plus 1, because in this problem n is equal to 4. 2n is equal to 4 here, and therefore n is equal to 2, and so 2n minus 1 will be equal to 3. So using that result you can write here this will be 4 pi a cube into 3 divided by 8, you can do the algebra, into root over pi divided by b to the power 5. b to the power 5. Now we can see the relation between a and b is what? You can see that this a is equal to root over b over pi, and you have seen that this constant b is equal to m over 2 kT, where you know that k is Boltzmann constant and T is absolute temperature. And therefore substituting these values in the above result, you can see what will be this v bar square. So see here, as v bar square is 4 pi a cube times 3 by 8, 4 pi a cube. So we will write 4 pi a cube, and a cube will be equal to b to the power 3 by 2 over pi to the power 3 by 2. So this is b to the power 3 by 2 over pi raised to the power 3 by 2, and times 3 over 8. And again you can see under a square root there is pi over b to the power 5. So you can write it as pi raised to the power half over b raised to the power 5 by 2. Now you can simplify it, and after simplification you will get readily that this is nothing but 3 divided by 2b. And when you will substitute the value of this b here, what will be your result? You can see this is 3 by 2, and 1 over b will be equal to 2 kT over m. So this 2 and this 2 will cancel out, and you get that this v bar square is equal to 3 kT over m. Actually this result we have already obtained while determining or evaluating the values of constants a and b. In fact, this is just a repetition. I have already calculated this result earlier. So we get here the value of the mean square speed, and you know from the definition of RMS speed what will be the value of RMS speed as defined in equation 1. Therefore you can say RMS speed is, you have seen earlier that this Vrms is simply equal to a square root of V bar square. So you can see that this Vrms is simply equal to a square root of 3 kT over m. So we have obtained very easily using the Maxwell's distribution law the expression for Vrms. And one thing here is very remarkable, that this Vrms depends on strongly depends on temperature T. So you can see here that this Vrms is proportional to a square root of T. So if you consider that this T is equal to 0 K, that is you are considering that temperature is absolute 0, then what will be the value of Vrms? You can see this Vrms will be equal to 0. And this is why, in accordance with the classical kinetic theory, we say that at absolute 0 all molecules are at rest, because you can see here this Vrms becomes 0 when temperature is 0 Kelvin. I hope you have understand clearly how we can find the expression for Vrms. Now let us see the another value of speed will be which we have to evaluate, and that another value you know is average speed or mean speed. Now we are going to find the expression for average speed, or you can say mean speed. Average or mean speed. In fact, if you have learned the steps in the previous section, you can easily find the average or mean speed in this case. When you say average speed, just like the mean square speed, you can define it that average speed will be simply equal to sum of the speed, not a square, sum of the speed of the all molecules divided by the total number of molecules. So if you denote this average speed by the symbol V bar, then this V bar will be defined how? This will be equal to sum of the speeds, sum of the speeds of total molecules, divided by the total number of molecules. And as you have seen that this dNV denotes the number of molecules having a speed between V and V plus dV, and as earlier I have told you that dV is very small, so almost a speed of each molecule is equal to V. So if we want to calculate the number of molecules, the sum of the speed of molecules whose number is dNV, then we will simply multiply V by this dNV. So V into dNV, this will give the sum of the speed of dNV molecules. And when you will integrate it between the limits 0 and infinity, then you will get the sum of the speeds of the total molecules. So this is sum of the speeds of total molecules will be integral 0 to infinity V into dNV. And then we will divide it by the total number of molecules, which is n. So you can say that this V average, which is denoted by this V bar, is equal to integral 0 to infinity V dNV over n. Now again you can see, according to Maxwell's law of distribution of molecular speed, this dNV is equal to 4 pi n a cube times e raised to the power minus bv square times v square dv. So now let us substitute this value of d and v here, and therefore you can write that this v bar is equal to 1 over n integral 0 to infinity v times 4 pi n a cube times e raised to the power minus bv square times v square dv. Again, we will take this constant factor 4 pi n a cube outside of the integral, and when you will do it, you can see the n in the numerator and n in the denominator will cancel out, and what will be your result? This will be simply 4 pi a cube times integral 0 to infinity. Now you can see this is e raised to the power minus bv square, and this v and v square will be v cube now, v cube dv. Again you can see here actually this is a Gaussian integral, and at the place of x there is v, and this v contains the power 3. So at the place of 2n plus 1 there is 3, and so n will be equal to 1. And so you can use the Gaussian integral formula which I have mentioned here. I am showing that result again to you. You can see this is the formula which will be now applied. In fact, in this case we have n equal to 1. So using the value of n equal to 1, you can easily write the value of this integral. So now let us write the value of this integral. Therefore, you can say that this v bar is equal to 4 pi a cube 4 pi a cube times n factorial. N factorial means here 1 factorial over 2b raised to the power 2n plus 1. So this will be 2 into 1 plus 1. So this is 4 pi a cube times, you know 1 factorial is simply 1, and this will be, sorry, here is not 2n plus 1, but there is n plus 1. N plus 1. And you know that n is in this case equal to 1. So this is 1 plus 1. 1 plus 1. And so this is 2b square. Again, you can put the values of a and b. Now we know that a is equal to b over pi whole to the power half, and again you have seen that b is equal to m over 2 kt. So we will now substitute these values. This v bar will be equal to what? This is 4 pi a cube, and a cube means you can see from here this will be b to the power 3 by 2 times over pi raised to the power 3 by 2 and into 1 over 2b square. 1 over 2b square. So you can now see that this will be what? This will be 2, and here is pi, and this pi, and in denominator there is 3 pi raised to the power 3 by 2. So this will be in fact pi raised to the power half. And you can see in numerator there is b to the power 3 by 2, and in denominator there is b square. So we will left here 1 over b to the power half. So this is simply 2 over pi b square root. And when we will put actually the value of this b, what will be our result? You can see this will be 2 over pi times b, and b is m over 2 kt square root. So if you simplify it, you will get actually this will be 8 kt over pi m's square root. Actually I have included this 2 inside the square root, making it 4. So what you get here, you can see we get that the value of the average speed is simply a square root of 8 kt over pi m. 8 kt over pi m. This is the value of the average speed of molecules of a perfect gas. Now again you can see that this V average is directly proportional to a square root of T. So if this T will be equal to 0K, that is temperature is absolute 0, then you can see like Vrms, this V average is also 0. So at absolute 0 temperature, the average speed of molecule of a perfect gas is also 0. Now finally we have to obtain the expression for the most probable speed. Actually we have seen in the discussion of Maxwell's law of molecular distribution of speed that this most probable speed actually corresponds to the point in the Maxwellian distribution curve for which the Maxwellian distribution function fv was actually maximum. You have seen in this graph that graph was like this. In fact here we note v, and on this axis we note fv, and fv is Maxwell's distribution function for molecular speed. And you have seen what is this fv. You know fv, as I have mentioned here, you can see and you can remember that fv is equal to what? This fv is equal to this much, you can see here. So noting the value of fv, you can easily find the expression for the most probable speed. So first of all, let us write the heading because we are going to now find the expression for most probable speed. Most probable speed. Most probable speed. Because you know that this fv is equal to what? This is 4 pi n a cube e raised to the power minus bv square times v square. This is the value of fv. And you have seen the speed of the molecule corresponding to the maximum value of this fv is simply known as most probable speed. This is known as most probable speed. Actually, this is the maximum value. So you have seen earlier that when Fv is equal to Fv max, then this V is equal to Vmp. You have seen earlier. So we will simply apply the condition for maxima, and you know from calculus that if this Fv is maximum, then definitely its first order derivative will be equal to 0. So when Fv is maximum, then you can say that then dFv by dV, this will be equal to 0. So now let us substitute the value of Fv and simply differentiate it and simplify. You will get the expression for the most probable speed. So you can see this is d dV, and again we will substitute this value of Fv, which I have just defined here. This is 4 pi n a cube e raised to the power minus bv square times v square, and this will be equal to 0. You can see this 4 pi n a cube is a constant factor, so we will take it outside of the differential operator. So this implies that 4 pi n a cube, this is outside of the differential operator, and this is d dv, and inside the square bracket the remaining factors are what? You can see this is e raised to the power minus bv square times v square. So you can write it, this is v square times e raised to the power minus bv square, and this will be equal to 0. Now you can see, since in RHS there is 0, so when you will divide this 0 by this factor 4 pi n a cube, your result will be simply 0. So you may write this is d dv v square times e raised to the power minus bv square. This is equal to 0. Now you can see in the square bracket there is a product of two functions. So for differentiation we will follow the rules for the product of two functions. So let us differentiate it. So you can see the first of all we will take differential of this v square. So dc of this v square with respect to v will be equal to 2v. So dc of first function times second function. Second function is e raised to the power minus bv square, and plus now we will keep this v square factor at each, and we will differentiate e raised to the power minus bv square. So what will be this? This will be e raised to the power minus bv square at times minus 2bv, and this will be equal to 0. So you can see that this 2v into e raised to the power minus bv square may be taken as a common factor. So take it as a common factor. 2v into e raised to the power minus bv square, we take it as a common factor. So at the place of first term there will be simply 1, and now let us see what remains at the place of second term. As we have taken 2v times e raised to the power minus bv square as a common factor, so the remaining term will be minus b into v, and that will be equal to, so here is, yes, this will be actually equal to v square, sorry, this will be v square, because here is v square, so this equal to 0. Now you can see from here that this factor in outside, this factor will be 0 in only in two conditions. So if v is equal to 0 or v is equal to infinity, then in these two conditions, this 2v into e raised to the power minus bv square will be equal to 0. Because when v is 0, then due to this factor v, it will be 0. And when v will be infinity, then due to this exponential factor, this will be a 0, because then taking v equal to infinity, we will have e raised to the power minus infinity. And you know e raised to the power minus infinity is 0. So you cannot say that this outside factor is always 0. It is in fact, it can be only 0 when either v is 0 or v is infinity, but our result is always 0. So what we conclude from here? Since this outside factor is not 0 always, so definitely this factor inside the square bracket must be 0 always. So therefore you can say that 1 minus bv square must be 0. And if it is 0, you can see from here that bv square will be equal to 1, and so this v will be equal to 1 over b square root. But what is this v? As you have considered the condition of maxima of fv, and you know that when fv is maximum, then v is simply equal to the most probable speed. So definitely we will recognize this speed v as most probable speed. So you can say, therefore, the most probable speed, we denote it by the symbol Vmp, and you can see this will be a square root of 1 over b. And now let us substitute the value of b. You know that b is equal to m over 2 kt. So when you will substitute this value of b here, you will get that Vmp is equal to 2 kt over m's square root. So you have obtained the expression for the most probable speed here. And again you can see that this most probable speed Vmp is also proportional to a square root of t. And so you can see, if T will be equal to 0 Kelvin, that is our gas is at absolute 0 temperature, then this most probable speed is also 0, like the average speed and like the RMS speed. So finally we conclude, according to this classical theory of kinetic theory of gases, that at absolute 0 actually all the molecules of the gas are at rest. Although quantum mechanically this is not correct, but we are here considering the classical physics. So in classical physics you can say at absolute 0 temperature the molecules have no motion, neither translational motion nor rotational or vibrational motion. But according to quantum mechanics, even at absolute 0 temperature the vibration is not stopped, and so the vibrational motion takes place and the molecule has vibrational energy. But we are here considering the classical problem, so you can say that classically at absolute 0 temperature the molecules of a perfect gas are in fact motionless. Now you can compare the values of all these speeds, that is RMS speed and average speed and the most probable speed. When you will compare it, you will find that actually this Vmp is the least value, and after that you will get this V average, and finally the Vrms. So RMS value of a speed at a given temperature is highest, and after that the value of a V average is lying between these two values. So VMP you can say is less than V bar, and this is less than Vrms. I hope you have understand each and every step of the calculation. So definitely watch this and revise this and try to understand and write down yourself all these derivations. So now Maxwell's speed distribution law is completed, and hence in the forthcoming lecture we will consider some of the important illustrative examples or numerical problems which is very important for various examinations.